One of the biggest goals of statistics is to make predictions about a population based off of the sample. And we're finally at that now. We're looking at a skill set called confidence intervals for proportions. The model that we have for p hat, this will be the foundation for coming up with these guessing intervals. Its p hat is normally distributed with the center of p and a standard deviation of the square root of pq over n. So what this model does is it takes information about a population P and it spits out what should happen for a sample success rate P hat. Again, this is the opposite of what we want to be able to do. I want to start with the sample and figure out what's going on for a population. All the same, this is a good stepping stone. There are three assumptions for using this model. Random, by that I mean no bias. Independence, one thing does not affect another, or I sample less than 10% of the population and I can assume that things are spread out enough they don't affect each other. And finally, large N. I need to have at least 10 expected successes and at least 10 expected failures. Let's go ahead and see how we can make predictions about samples based off of populations using this model. And again, this is sort of like the complete opposite of where I want to end up, but it's going to get us thinking in the right way. We're told that a coin is fair. All right, let's break that down already. If it's fair, I should get heads 50% of the time, and I should get tails 50% of the time, with 68% certainty. I'm just going to underline that. I'm remembering the 68 from that lesson on the normal distribution, but we'll cycle back to it. What proportion of the time should we get heads? So what is my p hat if I'm looking at n equals 100 flips? Okay. Well, the model I know, my sample success rate should be normally distributed with the center of p. So plugging in that value into this equation here, I expect that when I flip a coin 100 times, my success rate is probably going to be close to 50%. Sometimes it's going to be higher than 50%, and sometimes it's going to be lower, but ballpark around that number. My standard deviation is going to be the square root of my p, 0.5, my q, 0.5, all over my n of 100. When I type this into a calculator, I end up getting a standard deviation of 0.05 or so. So I'm expecting a 50% success rate, give or take 5%. So trying to visualize this, this is the graph of every possible success rate I can have when I'm looking at 100 flips. And by far, the most likely outcome is going to be half and half. I'm counting by 5%, so 55% and 45% are still considered usual. 2 standard deviations, this is the cutoff for unusual. And while it's possible to get something lower than 40% and higher than 60%, that's starting to become a rare outcome at that point. Now, as I'm looking at this, if I'm wondering what the likelihood is to be in any given region, there should be a percent confidence that's linked to that. For example, remembering earlier from that normal distribution lesson, I have the 68, 95, 99.7 rule. Within 1 standard deviation, I have 68% of my data. Within 2 standard deviations, I have 95% of my data. And within 3 standard deviations, I have about 99.7% of my data. For this one, I want to be 68% sure or 68% confident. So this means I want to be within 1 standard deviation of the center. So from 50%, I'm going to go up and down 1 of these standard deviations. And I can see that on my graph already. Actually, I shaded that in somewhat intuitively there. It appears to be anything between 45 and 55. So what this means is I am 68% sure that if someone went out and started flipping a coin 100 times, that they would get something between 45 and 55. I have now some predictive power to guess what should happen for these samples based off of the claim that the coin is fair. 68% for me, I'm not sure how comfortable I would be with that. I feel like there's still a high risk of being wrong there. So instead of being 68, let's say I wanted to be 95% certain. Well, my big difference here is to be 90% certain or 95% confident. I'm creating intervals that I am confident in. This would be within 2 standard deviations of the center. So I'm going to go from the middle, 50%, and I'm going to go up and down 2 of those standard deviations. This is going to give me a low value of, and I can actually see it on the graph too, 1, 2 tick marks down is 40, 1, 2 tick marks up is 60, or from the formula 2 times 5 is 10, so I have 50 minus 10, 40, 50 plus 10, 60. Looks like I have an interval from 40% to 60%. My sentence that would go along with this is I am 95% confident that the interval of 40% to 60% contains the percent of heads in 100 flips. If I wanted to be 99.7% sure, almost entirely confident there in what should happen, I could just go out 1 more standard deviation. So this amount that I'm multiplying this standard deviation by, this is really controlling how sure I am in these guesses. And in general, if I want to be more sure of myself, I should guess more values. Think of it as like buying lottery tickets. The more lottery tickets you buy, the more guesses you make, the higher your chances are of winning that thing. I don't recommend doing that. You may have noticed in this last problem, I really hope you noticed, the only difference between each of these scenarios was that number next to my standard deviation, and that number is called the critical value, or the Z star. So our critical value, if I want to be 95% confident, is 1. So this means I would go both up and down 1 standard deviation from the center. So a Z star is sort of a 2-directional thing. It's telling me the amount I need to go in both directions there. If I wanted to be 2 for 95, if I wanted to be 68% confident, that's 1 standard deviation. If I wanted to be 99.7% confident, that's 3 standard deviations. So the 68, 95, 99.7 rule can be really rephrased as being within 1, 2, or 3 standard deviations away from the center. With this in mind, let's kick our interval up a notch, and let's be 99.7% confident now. So my thought process is I'm going to go from the center up and down 3 standard deviations. The center of my model, I was expecting 50%. My standard deviation was 5%. So from 50%, I'm going up and down 15%. 3 times 5 gives me that 15% there. So on the low side, I get 35. And on the high side, I get 65. So my sentence that would go along with this, I am 99.7% confident that someone would get heads between 35% to 65% of the time if they're looking at 100 flips. So in other words, it's extraordinarily unlikely that I would see someone end up with, say, a success rate of 72%. This interval is allowing me to predict the future based off this population value. I'm going to do the same thing now with symbols, so I can just have like the most generic guessing window possible. So I'm calling this a confidence interval or a guessing window. And I will abbreviate confidence interval as CI for what should happen for my sample success rate. And this should be my center plus or minus some number of standard deviations. Now, the formula that I'm looking at here, my center and my standard deviation, that came from this p-hat model. So my center is p, and my standard deviation came from the square root of pq over n. So kind of doing a remix of that first formula. So I have p plus or minus c star, and then I have a big square root here, pq over n. Okay, sorry about the mess there. I have p plus or minus z star square root pq over n. And again, this is the opposite of what I actually want for an interval. I want to be able to guess what I should be getting for p if I'm plugging in stuff for p hat. All the same, I like this interval so much that I actually typed this at the top of this next page. So for those of you that had a hard time reading that scratch writing, I've got it nice and pretty on this next page. Okay. Two quick diversions here, thought exercises, making sure I'm feeling comfortable about stuff, and then let's try to see if I can do the same thing in the opposite direction. So suppose that Michael lives within 3 miles of Kara. Knowing this, do you think Kara lives within 3 miles of Michael? I want you to think about this. I'm not trying to trick you when I ask you this question. This is a question that I feel like I can ask pretty much anyone I know, and they would be able to give me a response without overthinking it. So don't overthink this, but pause the video. If Michael lives within 3 miles of Kara, does Kara live within 3 miles of Michael? Okay, and I'm really hoping that if you realize Michael is within 3 of Kara, then that's also reflexive. So that means that Kara is within 3 of Michael. So this is true, or yes. Now, some of you might have gotten into some really technical situations where like, well, maybe there are one-way roads where due to the way that the city's set up, it takes 3 miles to go one direction, but 2.9 the other. Fine. Then we can say, yes, this is true, assuming two-way roads. So I have some sort of a way of switching the names of things in a distance sentence and keeping that true. Let's look at another example. We expect p to be within 3 standard deviations of p hat with 99.7% certainty. Do we expect p hat to be within 3 standard deviations of p, also with 99.7% certainty? Go ahead and pause the video and try this out, or I'm just going to doodle a little bit on the page here while you think through things. I'm going to rename things for my own benefit, try to make it easier for me. But think about this problem and see if you can come up with an answer. I'm going to name P Michael classic Michael name. I think standard deviation is a little bit confusing for me, so I'm going to call that miles instead. I hope you're okay with that. And this p hat symbol is kind of tripping me up. So instead of that, I'm going to call this Kara. Just giving these things different names. Still means the same thing. I'm just changing the language a little bit. And let me read it. We expect Michael to be within 3 miles of Kara. Do we expect Kara to be within 3 miles of Michael? Oh, shoot, this is the same thing. So this statement here is the same thing as asking if we think Michael and Kara living within 3 miles of each other means that Kara and Michael live within 3 miles of each other. This is true in almost in an empty sentence kind of way. So yes. And if you're worried about those two-way roads, well, I have the roads up here. I have addition. The opposite of addition is subtraction. I have subtraction. The opposite of subtraction is addition. I have a way of getting rid of a square root. I can square things. I have ways of getting rid of multiplication, division. And I have ways of getting rid of division. I have two-way roads. So yes, I can switch P and P hat. These are just names in a distance sentence. So let's keep that in mind. If I have some sort of a setup, some sort of a sentence, just like I do here, that has P and P hat, I should be able to switch those symbols. And we're so close. Okay. So far, my confidence interval for my sample success rate is P plus or minus C star square root PQ over N. This looks really nice. Now, what I want to do is create an interval for my population success rate, and I want it to be based off of the sample. So this is what I'm going to do. I'm going to take the sentence that I have up here, and I'm going to switch every place where I see a P hat for P, and I'm going to switch every spot where I have P for P hat. So confidence interval for, I'm looking at population now, will be P, well, I'm going to switch the symbol, so this is now a P hat, plus or minus Z star square root, used to be P, now it's based off of the sample, P hat. N is my number of samples, I'm not worried about that. Q is my population failure rate. Q with a hat will be my sample failure rate. So my confidence interval for a population proportion is going to be P hat plus or minus C star square root P hat Q hat over N. I've worked very hard this term to get this formula, and I'm excited to use this thing now. There are 3 assumptions for using this model. First one is I have a random sample. Next one is that I have independence between trials, or the 10% rule. And if these things are looking familiar, it's because it is exactly the same formula that we started out with at the beginning. I have random, I have independence, or the 10% rule, and my last one's going to be large N. And a reminder, large N was N times P bigger than or equal to 10, and N times Q bigger than or equal to 10. Now, just as a quick note here, I have switched all of my P's for P hats, so my assumptions here, since I'm plugging in P hats into the equation, my assumption check should be based off of the hat data as well. Here's what this means. When I was looking earlier at N times P and N times Q being bigger than or equal to 10, this was the expected number of successes and failures. In contrast, when I'm dealing with confidence intervals, this isn't based off of what I expect, it's based off of what I experience. So this is 10 actual successes and failures. It's something that you can easily count. Let me show you what I mean by that. Create a 95% confidence interval for the true proportion of PCC students that own a TI-89 if 15 out of 60 sampled students own a TI-89. Okay, my number of successes, 15. That's bigger than 10. My number of failures, this is out of 60 trials, so if I have 15 successes, I have 45 failures. That's also bigger than 10. My large N assumption becomes pretty easy to check here. I want to be 95% confident. So for my critical value for 95%, I'm going to go up and down about 2 standard deviations. And the formula I'm going to use for the confidence interval for the true proportion of PCC students that own a TI-89 calculator is going to be my success rate plus or minus my critical value times the square root of my success rate, my failure rate, over the number of samples. Okay, p hat. So I had 15 out of 60 as my sample success rate. So I'm going to type that into a calculator and I'll see what I get. This gives me 0.25. If I have a 25% success rate, that must mean I have a 75% sample failure rate. Plugging these values into this formula, I expect about 25% of these students will have this type of a calculator. My Z star, my critical value, is going to be 2. And my P hat, 0.25. My Q hat, 0.75. And my M, this is out of 60 trials. I'm going to type this into a calculator and I'll see what I get for a low value and for a high value. So I have 0.25 minus 2 times the square root of 0.25 times 0.75 over 60. I'm typing this thing in once with a minus sign here. This gives me 0.138. A little bit of a graphing calculator trick. On most graphing calculators, if you hit second and then the enter button, it pulls in the last thing you typed in. You can also use the up arrows to select it. And I'm going to change that minus sign to a plus sign to get the high part of my interval. So I got 13.8 to 36.2% or so. I'm going to write out the sentence that goes along with this. We are 95% confident that the interval of 13.8% to 36.2% contains the population or overall percent of PCC students with a TI-89. So if you ask me, do I think it's likely or not likely that the majority of students have a TI-89? I would say, well, I don't think that's likely at all. I'm anticipating, I'm 95% sure, I could be wrong, but I'm 95% sure that I should get something between 13.8 and 36.2. Now, let's say you want to be even more confident. Let's say you want to be 99% sure. Unfortunately, I don't know how to do that yet, though. I only know how to do 68, 95, and 99.7. So I'm going to come back to 99. And for now, instead, let's be 99.7% confident. So I just did this being 95% sure. Let's now be 99.7% sure. My sample success rate is still 25. This means I expect about 25% of PCC students to have this type of a calculator, give or take something. My Q hat is 0.75. I have 60 samples, and my critical value for 99.7 is approximately 3. So setting up my interval again, I'm going to have my center plus or minus my critical value times my standard deviation like thing. My center is 0.25. My z star is 3. 0.25, 0.75 over 60. If you struggle typing that whole thing into your calculator at once, it's totally okay to kind of break this up into smaller pieces. So for example, let's just type the square root value inside of our calculator and see what we get for that little step. 0.25 times 0.75 over 60. And if you're comfortable with doing the whole thing at once, then go for it. I'm just trying to show you that you can break it up into smaller steps if you're not comfortable making that big step. Likewise, I can multiply this by that 3 to get the amount that I'm adding and subtracting to my estimates. So I have 25%, give or take 16.8%. Let's see what this gives me for my low value and my high value. And let's think about what's going on here as well. So I was 95%, I'm now 99.7% sure. If I want to be more sure, I have to guess more values. So this is a trade-off. My accuracy kind of drops. I like having nice guessing windows because if I just say, I don't know, the percentage is between 0 and 100%, that's not useful. So it's nice to have a small interval that you feel really confident in. So for this 1.25 minus 0.168, on the low value, I have 8%. On the high, I have 41.8%. So here's the downside. I'm really sure that it's somewhere between 8% and 42%, but that's a massive range of values. I don't feel like I've actually pinned that down all that well. So even though I'm more confident, I'm less precise. So word of warning, as we increase our confidence level, our interval grows as well. So we have to guess more values in order to be more likely to guess the correct thing. So it's a bit of a trade-off between the two. And in general, when I'm looking at these intervals, it's always some sort of initial guess, say 25%, give or take, however much error you're willing to have in those estimates. The technical name for this error is the margin of error. So looking at this last problem here, where we had 0.25 plus or minus 0.168, this 25%, this was my estimate for what the percentage should be overall. And the amount that I was adding and subtracting, everything after that symbol, this is the error in my estimate, or the margin of error. If you listen to the news or watch the news anytime near an election cycle, you'll see a lot of things like there's a current poll that indicates a 45% approval rating, give or take a margin of error of 8%. So they're meaning from whatever number they're telling you, they're willing to go up and down 8% for the error amount. Margin of error is the amount I add and subtract. A pilot study indicates that 25% of students have used the Student Learning Center. The researcher wants to continue to sample individuals until they can estimate the true proportion of all PCC students that use the SLC within 1% with 95% confidence. How many samples are needed? So this one kind of goes backwards. It's saying, I only want to have 1% of error. So the margin of error, the amount that they're willing to be off by, is 1%. And they want to be off by 1% with 95% confidence. If I'm 95% sure, that's giving me a critical value or a z-score of about 268, 95, 99.7. That's the 2 part of that rule. It's saying indicates 25% have used it, so this tells me my sample success rate is 25%. So my failure rate should be about 75% or so. So I want to see if I can take this information to figure out how many samples they're going to need in order to get this desired mO. So let's set up the formula. I'm taking my confidence interval and I want it to be within %. So I want the amount that I'm adding and subtracting, that part of the equation, to be equal to 1%. So 0.01, my mO, is equal to z star square root p hat q hat over n. And let's plug in everything we know. My critical value is 2 or so. My p hat is 25%. My q hat is 75%. And I do not know the number of samples, that's n. I've done the setup and I've now changed this from a Math 243 style statistic question into just an algebra one. And let's go through the steps. I want to get rid of this multiplication. I'm going to do so by dividing this 2 over. Whenever I'm solving, I'm always thinking opposites. I've got a square root. I need to think, what's the opposite of a square root? Well, that's squaring. So I'm going to square both the top and the bottom of that fraction. Squaring gets rid of the square root on the other side. Okay, for my next step, when I have a fraction equaling a fraction, a really good technique that you may have learned is called cross multiplication. And that's where you take the bottoms of these denominators and you multiply them both across the equal sign. This is not the only way to solve this. I'm just trying to give you a consistent process that will work. So I have 0.01 squared, and this n is getting multiplied over. This 2 squared gets multiplied over there, times 0.25 times 0.75. Finally, I want to undo this multiplication. This 0.01 squared is just a number, so I'm going to divide this over. And this tells me the number of samples that I need in order to have a 1% margin of error with 95% confidence. If my sample success rate is 25%, will be given by that expression. I'm typing that into a calculator. 2 squared times 0.25 times 0.75 divided by 0.01 squared. And when I do that, I get an n of 7,500. And it's a really, really good idea to know how many samples you're going to need ahead of time before you go out there and just start asking random people. Because suppose you ask 500 people and you're like, well, that should be enough. And you calculate the numbers and you see that you're not even close. If you keep going out again and again and again until you finally hit the required number, that might take you considerably more time, money, and energy than you might think. So solving for the sample size that you need to get a certain level of accuracy is a really good indicator of how much work you would have to actually do if you were going to collect these samples by hand. Okay, I know that we already have the ability to make these guesses, I want to continue practicing my language some more. So I'm going to take my interval that I had from example 7, where I'm creating a 99% confidence interval with x equals 15 and n equals 60. And again, I can't quite do 99%. That's driving me a little bit crazy. I want to be able to do any percentage. Right now, the best I can do is 99.7%. And our interval for that problem was our sample success rate, p hat, plus or minus our z star, square root, p hat, q hat over n. We plugged in our 25% for our p hat. That was a 15 out of 60 number. We plugged 3 in for our z star. And we plugged in 25 for p hat, 75 for q hat, and 60 for the n. So I'm just going to label this thing with all the vocab things you might get hit by. I said this 25% was an estimate for how many people had TI-89s. So I would call this my best point estimate. I'm guessing what the success rate is for the entire population using only one point or only one number. So 25% or so. The or so amount, everything after the plus or minus, is called the margin of error. Breaking the margin of error up, this 3 represents my critical value. It's how many standard deviations up and down I need to go for a certain level of confidence. And this square root, this is determining how much error I have in my estimate. So this is the standard deviation that determines how much error I have. So I'm going to call this the standard error. It's pretty much a standard deviation, but I'm plugging in p hat and q hat instead of p and q. So here's the difference between the two. Standard deviations are p's and q's. Standard errors are p hats and q hats. I use standard deviations when I'm doing stuff like hypothesis test. I have standard errors whenever this is part of a margin of error equation. The language here is not super important. It's not anything to get bogged down by, but I want you to have exposure to it. So that way, when you start to see these phrases show up in literature and research, you know what they're talking about. When I typed this into my calculator, I ended up getting 0.168 when I multiplied the critical value and the standard error, and that gave me the amount I was adding and subtracting. That gave me my margin of error. When I did the subtraction, on the low end, I got 0.082, and on the high end, I got 0.418. This final result down here was my confidence interval itself. So here's just a problem that goes through all of that different vocab in one spot. This way it could serve as a little reference guide as you're working through problems. Okay, one thing that continues to bug me a lot here is I want to be able to be 99 or say 90% sure. And right now I'm really limited in only being 68, 95, or 99.7% confident. I'd like to fix that. So how do I find z star for 90, 95, 99, any level of percentage I am worried about or care about? Well, let's think it through. And I'm going to need my normal table or some sort of technology to do this. To find z star for 90%, z star is the number of standard deviations I need to go up and down, and C is the area I have in the center of my curve. So I'm trying to figure out how many standard deviations I need to go up and down to have 90% in the center. Now I just want to take a look at my normal table here, and I'm noticing that this normal table is shaded strictly to the left. So if I want to be able to use this thing, it's not helpful having this middle area. I really need to know how big is this tail, and can I use that to look up this z-score? So let's think through that process together. If I have 90% in the center, then the amount I have in both of my tails, I'm using this alpha symbol to be the area I have in both tails. I have 100% take away the middle amount gives me 10% inside of both of those tails together. So 90% leaves me with 10%. If I only wanted one tail, I would take this 10% and I would split that in half. So in this case, if I have 10% in total, that tells me I have 5% in each of these tails. Since I know I have 5% inside of this tail, I'm going to look up this alpha over 2, 5% value inside of my table to come up with the z-score. So I'm going to scroll along on the inside here until I get as close as I possibly can to 0.05. And I see 0.0495, that's pretty close. I see 0.0505, that's also pretty close. So maybe somewhere between these things. So let's see what those numbers are. Negative 1.64, negative 1.65. It's somewhere between those two numbers. So a little bit of compromise, negative 1.6 between the 4 and the 5. So we'll say negative 1.645. Now z star is the amount that I'm going both up and down. So my z star in this case will be 1.645 if I want to be 90% confident. So here's my process. I start with the area C in the middle, 90%. I determine the area in both tails, 10%. I split that in half to get the size of just the left tail, because my table is shaded to the left, so it has to be shaded to the left. And then using the table, I go in the inverted normal direction. So I find the area on the inside to get that z-score. And finally, my z star is the amount I go up and down. So I wouldn't say stuff like I'm negative 1 mile away. I would just say I'm 1 mile away. Let's do another example. "95%. So I have 95% in the center. And I'm just thinking through this process here, because once you get the hang of it, I don't have to write down necessarily all these steps. I can kind of visualize it on the curve. If I have 95% in the center, this tells me that for both tails, my leftover area is about 5%, 1 minus. So if I want the size of the left tail, this is going to equal that 5% divided by 2, which gives me 0.025. So once I have the size of both tails, I split this thing in half. To get the size of just one tail. And now I'm going to try to find this inside of the table to see what the z-score is if the inside area is 0.025. So I'm going to scroll along and see if I can get close to it. 0.0244, that's pretty close. Oh, 0.025. That looks like it's spot on, 0.025. This is in the negative 1.9 row. This is in the 6th column. It looks like I have a z-score of negative 1.96. So this tells me that my z-star for 95% is approximately 1.96, or as we saw earlier, 2-ish if you're using that 68, 95, 99.7 rule. So if you want to be even more accurate than our earlier estimates, you can use this table to find the most accurate z-score you possibly can, at least up to 2 decimal spots. Z-star for 99% in the center. Okay, let's go through the process. 99% in the center, this is not to scale. This leaves me with 1% for both of my tails. So just one of those tails, I'm going to split that in half. That gives me 0.005, or 0.5% inside of both the left and the right tail. Since I know the size of this left tail, I'm going to look this up inside of my table, and I'm going to get as close as I possibly can to 0.005. And that looks like it happens somewhere between these two values, negative 2.57, negative 2.58. So inside of my table, I'm getting something of approximately negative 2.5, and I would take anything between the 7.8 and the 7.5. So negative 2.57-ish, 5 or so, compromising. So my z-star is approximately 2.575. Now, there's a video up on D2L, and if you're interested in this, I would encourage you to check it out. But there is a way to also do this using technology. The way that you end up doing this thing with technology is you do something called inverse norm. I'm going to very quickly show you how to do this on the TI-84. You go second vars, you do the inverse distribution, and instead of looking up this 0.005 on your table, when you're doing inverse norm, you're going to type in 0.005 as your area here. You're going to leave everything else alone. It's the tail that's to the left. And when I hit enter, this gives me negative 2.5758, which is remarkably close to my estimate. But this 8 is actually a round up situation. So let me adjust this and make this a 6 just to be a little bit more accurate. So if I wanted to be 90% confident, I'm using 1.645. 95% confident is 1.96. 99% confident has 2.576. I can now control any level of confidence for these intervals. So for example, let's say I had 100 Skittles that I tested, and I found that 15 of those were grape. So my success rate is 15%, and my failure rate is 85%. And I tested 100 candies. This says be 90% confident. And I now have the ability to do that. So in order to be 90% sure, I'm going to use this z-star of 1.645. But my confidence interval setup is going to stay the same. It's my best point estimate, my p-hat, plus or minus my critical value z-star, times my standard error, p-hat, q-hat, all over n. So I've got 15% plus or minus 1.645, 15, 85, 100, I'm going to type this in once with the minus and once with the plus. And then I'll write out the sentence. And then I will step back for a second and really look at what I've done. Because I think that we will have done something kind of incredible here. On the low end, I'm getting 9%. And on the high end, I'm getting 0.209 or so. The sentence would look like the following. We are 90% confident that the interval of 9.1% to 20.9% contains the percentage of grape Skittles. And here's the part that I just think is absolutely amazing. 100 samples. Based off of those 100 samples, I am coming up with a conclusion about grape Skittles worldwide. So I've taken a really limited amount of information about some sort of a statistic, and I blew that up to come up with some sort of conclusion about a population. The fact that we can do that is absolutely incredible, and it's only because of all those other skills that we've developed throughout the term. I hope you'll continue to practice this confidence interval material. I think you'll find that it's extraordinarily useful for figuring out what's going on with the world if you only have a limited amount of information.